Hello and welcome to Innovate and React. I'm Kevin Harris, and this episode will explore how solvents can activate reactants and allow a more efficient reaction. Today I'm with Nikolas Jankowski. Please tell us a bit about yourself.
Hello, Kevin. I studied with you, so we learned from each other from university. I then joined the organic chemistry department for my PhD. Professor Krause's working group works in metal catalysis, for example, gold catalysis, or mostly gold catalysis. And in the recent years, he took a turn more into sustainable chemistry, in which we explore water-soluble catalysts, for example, or micellar catalysis. In my master's thesis, I did some micellar catalysis, and this opened the field for catalysis for me in terms of academic research. Mm-hmm. And I was sure I wanted to explore more in my PhD, and especially in how to optimize reactions, which was a big part of it. And also, I wanted to do organic chemistry, basically, really build something from scratch and have some reaction mechanisms going.
Yeah, so also catalysis, which we talked about in the last episode. But this time, since it's more organic chemistry driven, it's much more complex molecules. Last time we had the aldol reaction, which is just two simple aldehydes combining, and there we don't have to look into many functional groups and stuff like that. So you mentioned that the optimization, that will also be one part. And first of all, what molecules did you look at?
So my professor liked to first build up some interesting substrate molecules and then do the last step as a gold catalysis. For me, it wasn't gold, but so therefore I synthesized propargylic amides, which is also quite, for me personally, it's nothing that special. They are built up from alkynes and amines, which are then subjected to a amide reaction, forming the propargylic amide, and this could then cyclize to oxazoles or oxazolines. That was my main topic. I explored different other substrate molecules as well, for example, allenes, which are even more difficult to synthesize. Well, someone who specializes in natural products will laugh, but to do four-step synthesis before you do the cyclization step, it's, some would say a waste of time, but then again, they are interesting molecules, right?
Yeah, exactly. In my synthesis in my PhD for the ligand synthesis, it was also like same amount, like 4 steps or so, but the actual reactions we looked at were then usually 1 or 2 steps at most, so that's the complete opposite of the spectrum. But you get, with more steps, to much more complicated molecules, and these are usually used for pharmaceuticals and plant protection, which have then a lot of functional groups. So here the catalysis is even more difficult because you have to see that you address only one functional group. In your case, the amide cyclization, right? So the oxazoles, what are they used for?
Yeah, so to make it short, really, there are some examples which are in the terms of pesticides, and there are some promising candidates in pharmaceuticals and so on, but as far as I know, there's not a real pharmaceutical right now on the market. Then again, it's a structural motif which you find in nature, and therefore it has the potential to be discovered. So the oxazoles are heterocycles which have the O in position 1 in the 5 ring, and the N, the nitrogen, in position 3. But there are other types which are isomers where the positions are 1 and 2, basically, right besides each other. Those are much more likely to be found in pharmaceuticals nowadays, and there is lots and lots of chemistry being done to build them in interesting pathways so that there's no selectivity issues.
How would you synthesize them in the, I would say, conventional way, when you just use organic chemistry and not catalysis?
Yeah, oxazoles can be found in natural products. So they have been isolated from plants and marine life. For example, there are some studies being done on primprenin or texamine, which have an oxazole motif, so the 1,3 heterocycle in there. And they were found to have some kind of improvement with hyperactivity, or they are working against tuberculosis bacteria. So there's that. But as far as I know, really a pharmaceutical agent is not currently in place. Maybe that's the reason why there's a kind of research gap where you can fit in nicely a PhD thesis. And well, there we are.
Yeah, nice. But the oxazoles, they then show biological activity because they are found in plants and marine life, as you said. But it's probably in very low concentrations, so we have to synthesize them if we want to use them as pest control or something like that, or antibacterial agents.
Right. There's one which is oxaprozin, which is a pharmaceutical, but as far as I know, one or two only candidates.
Yeah, but there's room for more, because once they have shown that they are biologically active, all the drug discovery tools, I guess, will pick them up, and then there might be future applications, and it is already good to have a synthesis plan for them. And how would you synthesize them in the classical organic chemistry way?
Yeah, so some name reactions. Obviously, we are talking about organic chemistry. There are two possibilities. One is Robinson-Gabriel synthesis, and the other one, the Fischer-Oxazole synthesis. The first one, Robinson-Gabriel, uses a dehydratization agent, something like a very strong acid, for example, sulfuric acid or thionyl chloride. They can be used. They are starting with some amide structure, as well as I had it, and then there is another ketone group in the molecule, which is then combined, and by the exclusion of water, the ring is formed from an oxazole. For the Fischer-Oxazole synthesis, you also use an acid for the reaction, and also displacement with water takes place. You need aldehyde for it, mostly aromatic ones, and also aromatic cyanhydrides. And those combine then to the oxazole as well.
Yeah, they all sound like they are itself very reactive, but now you say they need harsh conditions to have the specific reaction, I guess.
Right. They need quite harsh reaction conditions. The problem also is you need, at least for the Fischer-Oxazole synthesis, mostly aromatic ones, so you're limited in your substituents. And for the other one, dehydratization can also take place in other structures as well. So at the late stage cyclization method, this cannot be done. Not most of the time, but at least it's a concern.
So late stage in this context means that you have already a lot of reaction steps, and then later on you want to close the ring. That's not really possible with this kind of reaction.
Yeah.
Okay, got it.
Right. Yeah, and there was the idea from my professor, and he was like, okay, you see in the last decades or so, a colleague, Hashmi from Heidelberg, he published a lot of gold catalysis, and on this kind of reaction steps from propagylic amides, like I used, and then cyclized with gold to the oxazoles or oxazolines. And my professor was like, okay, as far as I know, there's not really a mild acidic reaction. Maybe we can look into this. Because obviously, if you use acidic reaction conditions, it's mostly not so expensive as you use a gold catalysis with special ligands and so on.
But with the conventional way, you have usually a lot of waste production, right? When you use quantitative amounts of acid, you end up with a lot of salts in the end. So that's why you usually want the catalysis.
Yeah, right. The gold catalysis is, maybe I talk about the history before my project again. Yeah, starting with those reactions like Robinson-Gabriel and Fischer-Oxazole synthesis, they require lots and lots of material, which then goes to waste, which is not sustainable. Therefore, catalysis is the next obvious step, going into producing less waste by catalysis, because you only need, 1% or so of it, and then there's a reaction taking place. Much more sustainable, comes with a cost, obviously. While this is maybe not always this much of an advantage in a lab scale, if it would be done in industrial settings, it's a no-brainer, basically.
Yeah. When you talk about tons and tons of product produced in the chemical industry, then you obviously also have a lot of salts. And also in the large-scale production, dealing with salts and solid material is much more difficult than when you have everything in the liquid phase.
Yeah, right.
So now we have the catalysis. And for oxazoles, there are also different kinds of catalytic reactions possible. You already mentioned gold and, if I heard correctly, also acid-catalyzed reactions.
Yeah, right. There are some other examples. You can use nickel, for example. You can use copper, iodine, or bases, depending on which structural motif you have, obviously, but there are some different possible ways. I would not say it's quite easy to make, but there are lots of ways to do it.
Yeah, but maybe they are limited, as you said. When depending on the structural motif, you can choose one. It would be nice to have like a more general tool. Transition metal catalysts usually have a high selectivity and high yield. How do they compare? Like in this case, gold with the other catalytic reactions?
Yeah. One really advantage of gold catalysis is that usually you have really selective reactions. There are not this many functional groups reacting with it. In my working group, usually you have something like an alene structure, alkynes, and so on, which I activated. That's a whole nother topic for nickel, for example, which just goes with everything. Then you have selectivity issues and have to find the right reaction conditions, which produce just your product selectively, as well as bases or acid catalysis. Yeah, they react with a lot of functional groups. So the more you have in your molecule, the more you're likely to produce byproducts, which you don't want. In the lab, you need
many of them.
You need so much of separation techniques.
Those would be better for like the early stage reactions when you just have some functional groups and then you use them. But in the end, you want high selectivity, because also when you have already a lot of steps and then you lose a big chunk of your product because of low reactivity, it also destroys a lot of your work.
Right. Yeah. And full disclaimer, I'm not entirely sure how well my project fits in there. Yeah. So, so to speak, it's a work of pure science. And that's a full disclaimer at first. I'm not entirely sure how well it's with every functional group. The scope you have in university is also somewhat limited, but I think it just gives some small edge in some ways. Yeah,
it's a different concept. We will talk about this in a moment. Well, first, one last question about the gold, because you wanted to substitute the gold with a different strategy. What are the problems with the gold catalysis. So we talked about all the benefits that we have, like high selectivity, high yield, and you can do this in a late stage synthesis. But what are the downsides?
So we use homogeneous catalysis for these reactions, and with this you always go or find yourself in some kind of separation issues. In the lab scale, maybe this is not of this much trouble, but later in industrial processes, it's a headache, really.
Yeah. Column chromatography is not really a thing in high amounts.
Yeah, and right, in pharmaceuticals, there are limits in which how many trace amounts of metals can be found or may be found, and so you really want to exclude.
You really want to avoid them.
Yeah, I think that's really the point. In if you do homogeneous metal catalysis, you really need to find good ways to separate a catalyst. So while in lab scale you can do homogeneous catalysis really well, it's oftentimes difficult in industrial settings. The separation is quite difficult because, as you said, you cannot do some column chromatography, or it's at least very, very expensive to do so. To get down to trace amounts, you often need multiple steps of crystallization, which is also time consuming.
That's also the reason why still some of these old conventional organic syntheses are still carried out in large scale, because they simply don't have a metal which you have to take care of later. If there's some acid left, you can deal with it and adjust the pH and filter out the salt or so. But the metals are really difficult to get out completely, so there are always some ppms left, but I think for some metals it's even like ppb level, which you have to make sure that there is not more than this, and that's really difficult. So yeah, in this case the best way is to not use the metal. And how did you try to tackle this problem?
Maybe I start from scratch. So when I wanted to start my PhD, I talked with my professor about my topic. I wanted to do some optimization work, so catalysis would be nice. I wanted to explore some kind of reactions. And he was like, okay, I think about it. And when we talked later about it, he came up with an interesting story of how when we did allenes, back in the day, you had to be really careful with your NMRs because the allenes cyclize in chloroform because the chloroform really slowly produces HCl. And this is enough to sometimes cyclize it. When they tried to replicate it in the lab, they found that the only sure way to make it is use chloroform and then put anhydrous hydrogen chloride gas into it.
Mm-hmm. Interesting. So if you use just normal hydrochloric acid, then it wouldn't work.
Right. Then you get some kind of ketones mostly, and not the cycle we wanted back then. So he asked me to look into this. He had one paper from Jeffrey Aubé, in which he used hexafluoroisopropanol and a sacrificial agent to produce anhydrous HCl in situ. This is where I started, and I then synthesized the allenes, which I then subjected to the method of Aubé. It is acetyl chloride in HFIP, which then undergoes a sacrificial reaction to produce HCl, which is the active molecule then.
What is the HFIP?
Hexafluoroisopropanol. Right. You know isopropanol, so rubbing alcohol, oftentimes called in the US, for example. There are 6 of the hydrogens are exchanged for fluorine atoms. So you have 2 CF3 groups in there, which have a very strong inductive effect, and therefore you have a different reactivity for the molecule. And most importantly, it pulls the electrons to the fluorine because of high electronegativity, and therefore you have a strong effect on the alcohol group.
Which makes it more acidic?
Which makes it more acidic, right.
And then you are using this as your solvent, and then the acidic solvent takes care of the reaction, or?
Right. So there is, in recent times, there's a lot of literature being produced using HFIP as a solvent because it has some interesting effects which come from the special structure or the special effects in there. And for example, OB in his paper, he used it for a Schmidt reaction.
What is the Schmidt reaction?
I shouldn't talk about reactions if I don't want to explain them, huh? Okay, so basically it's also some kind of, you have a ketone and azide. All right, so he used this for the Schmidt reaction, intramolecular one. And so the main catch is usually you need stoichiometric amounts of acid in there, very strong acids. But in his reaction, the HFIP was used as a solvent, and he found that it's coordinating on the ketone group, which then leads to a better or easier way of activating it. And therefore the reaction can take place in milder conditions.
And this kind of acid activation can also be used for the cycloisomerization that you looked into.
Right.
And how is this similar to the gold catalysis, or is this similar to gold in any way? Maybe
I would take some step back and start again with the allenes. So as my first project. So the allenes I then subjected to the method of OB, basically, and looked into what happens. And the first thing I learned is if you just do it like that, it turns to a brown sludge. The brown sludge really is some kind of following me around, I think. So through the 4 years of my PhD, I had so much brown sludge. I would go as far as to say that 1/3 of it was just that.
Yeah. And the off-white product.
Yeah, great. Don't look even further. And when we found reaction conditions which worked, it was not really this high of academic merits. It was like, okay, well, you do an acid catalyzed reaction, and that's not this special because there's no special reactivity in it. You still had to do column chromatography and so on, and it was like, okay, really, you're limited to special substrates of the allenes. You use a just normal acid pathway, and then you have also the separation issues.
So it is possible, but doesn't really offer any advantage over the
right. So I scrapped this.
Yeah. Well, that's also part of research. Sometimes you have to pull the string and decide that it's enough, and then you can focus your work onto other more promising work.
Yeah, right. And this was then for the propagilic amide cycloisomerization. I had the substrates from my master thesis already, so I could just threw them together and then look into it. And so that was really nice. And I found that there is a pathway. So it's not catalytic, unfortunately. So you have to get more than one equivalent of acid in there. But at least you could cyclize it. So objective one missed, not catalytic. But the other one was, okay, but it works.
Yeah.
So let's look further into it. And when we looked into this, the next step was obviously go back to literature and seek what you can find. Is there any acid catalysis or acid promoted reaction, really? And there is. So there are possibilities. For example, you could use my model substrate later in the optimization and just throw it in pure sulfuric acid. It works, but only for 50%. So at least this type is also limited because of the sulfuric acid, but also uses lots and lots of acid in it.
And has a low selectivity if only half of it is converted to the desired product.
Yeah, right. Right. And yeah, there are some other types. Again, every reaction has its limitations. And then we were like, okay, but there's nothing which is like the universal solution for this kind of problem.
Mm-hmm.
So we looked deeper into it, and we had then the HFIP as a solvent. We had acetyl chloride as sacrificial donor, and used this in the reaction. It worked out at a lot of substrates, different groups, but we were limited to terminal propyogenic amides at first.
Mm-hmm.
So the alkyne is a terminal one, having only one side substituted. With this, we had really a great success, different substrate, and you have two possible purification strategies. The first one is, well, just remove the solvent. The HCl goes with it. The acetyl chloride or the acetic acid, which is also formed when water is there, you can just get it out with a rotovap.
That's easy.
Yeah, and then you're left with oxazole salt, basically the HCl salt, and it was pure, 99%. The NMRs are really, really beautiful.
Nice.
There's nothing in there, just your molecule.
It's always
Quite happy about
satisfying
that.
to have a very pure NMR.
Yeah.
I can relate.
One of the peer reviewer for the paper later said like a really nice experimental, nice NMRs. So that was really good.
So you had a great starting point, which showed that it works for a lot of different substrates, but it was still in the start. So you had probably not the best conversion yet, or what was still to be optimized.
Okay, so with the model substrate, I did the first reactions in a microwave because, well, time is money also. And there the reaction works in under 1 hour. Mm-hmm. But I wanted to do, or my professor was like, yeah, that's fine. But then again, it's not that you are doing this special kind of super reaction. Do it the conventional way, then you have more of a selling point in it. Everyone should use it or should be able to use it, right? So I got back to the bench and looked into it with design of experiments. This was something I learned about in my master's thesis, or not the thesis, but in my practical course in your department, actually, in the technical chemistry department at our university, where you really have, you can use statistics for the analysis, and you don't need to do every possible reaction in every possible way, but you can apply statistics and go with less reactions, which is quite nice.
Yeah, DOE is short for design of experiments, right?
Yeah, and I found this tremendously helpful in my work in the master's thesis. I didn't use it then because of time constraints. I had very long thesis before I could apply it, and therefore, I skipped it, but I really wanted to do it in my PhD thesis.
Also, one really good advantage of the DOE is that you can find the optimal point and not just the local optimum point, because sometimes you screen in different steps and then you say, okay, on 3 equivalents of this reagent, it's the perfect amount, but the actual optimum is at 2.8. And that you would never find with just the screening. So this is also a big advantage. But why is DOE not used that much in the organic synthesis research?
I think it's just from historic pathway, basically. So the historic way to do a kind of optimization in the lab was OFAD approach, so one factor at a time. You would go first and select your, whatever it is, basically your equivalence of one reagent or the type of base or something like that, you would use just one. You would just vary one of the factors and then go through. And yeah, as you said, you're likely to miss the true optimum like that. And it's also not really concise. And if you have a large number of factors, it's really helpful.
You use design of experiments for your reactions, and what parameters did you optimize?
Yeah, my reaction was quite simple. You have an internal reaction, you have your solvent in different concentrations, temperature, time, and yeah, the sacrificial donor. So the main factors I identified was obviously the equivalence and the temperature. Then you have the minor ones, which are concentration and time is always a factor. Depending on in which direction you want to go, you can optimize for it or not, really. For me, for example, I looked into these factors. It's a small design, so it's equivalence of sacrificial donor, the temperature, concentration, and time. And with this, you have just 4 factors. You could do a full design. So it's 2 to the power of 4, so it's 16. 16 reactions is quite okay. You can do it in a lab easily.
Yeah, but if you have a lot of purification steps and all that, that also is time consuming, so you maybe want to reduce those as well.
Yeah, right. But for me at least, it was low enough that I choose a different way. I didn't do a screening design, but I did an optimization really. So a response surface where you get a curve of the reaction. So you have 3 points instead of 2. And with this, I optimized the reaction and got something about like 2 equivalents, 80 degrees Celsius, and 1.5 hours of reaction time.
What starting yield did you get before the optimization, and what was then the result of the optimization?
Now, before the optimization, I was under 100%. It was like, 70 or so, 60, depending on different factors. With the DOE, I also found some systemic error which was closing of the vessel. So you really had to make sure it's really airtight. Otherwise, you would lose some of the HCl. Yeah, it has to be a closed vessel. Then with this, after the optimization, I've got over 99% yield. So
that's great. Not
really
really
nice.
Not really better possible.
Yeah. And as I said, purification usually was just to remove the solvent for the hydrogen chloride salt, or do a basic wash up of it, and then you had the free oxazole.
Yeah, that's also very convenient when you compare the hours and hours for column chromatography and other synthesis.
Yeah.
You used also different acid donors in your reactions. Which was the best one?
Right. For every, if you want to do some kind of this optimization stuff, you should better work on, is this really a good one? Is this really the best you can achieve? So you would always choose to do control studies, doing the same type of reaction without the solvent or the special kind of solvent, but doing it in isopropanol, for example. For me, you get a lower yield in it. You would go do something like using the normal acid variant, the hydrous HCl, which is then in DCM, for example. There you also get the reaction going, but also not so selectively. Then you have some different reagents. The sacrificial donor could also be TMS chloride, so trimethylsilyl chloride, which is also undergoing the sacrificial reaction with HFIP. This one worked as well. So this would have been also a good reagent for this type of reaction.
But that was not optimized for, right?
Yeah, it was just the control studies, right? Yeah. Right. So with this, you test your way through it. Also without a reagent, for example, you would also make sure that you really have to use it. Yeah.
And then after you optimized the reaction, you used the optimized conditions for all different kinds of substrates and achieved a quite impressive scope for this reaction. In the beginning, we mentioned that a lot of these reactions were very limited in terms of the substrates.
Yeah, so to the scope, we try to use different ones. You always want to have some kind of different effects on the system. So we substituted at the amide side for different aromatic ones, different aliphatic ones. You want to use maybe very steric substituents. For example, we use adamantyl or an lauryl chain, so C11. I hope it was the right one. And also you have some kind of electronic effects there using fluorine groups, using nitro groups, and so on. And with this, you try to test your reaction if it's really worthwhile to do. So the very basic one, cooking, real cooking one. Give it to a student if he has some good hand in synthesis. And this worked really well. So I had also there very high conversion rates and isolated yields up to 99% or so as well.
So a great new tool for the synthesis of oxazoles, which is
definitely
then a big advantage compared to all the other reactions which are limited, and then you have to basically for each new product see, okay, which reaction can I use, which reaction might be problematic, and now you can just use your synthesis protocol and it works with most or many at least substrates.
It works for some substrates and I think it can be used for some different reactions. Also part of organic chemistry is oftentimes that you look into the reaction mechanism. I did it as well. So you wanted to see where's the hydrogen attacking most likely, where is it going? Is this incorporated into the molecule or not? Is it true catalytic as this, or is it just a promoted reaction? I would like to look into this. And we used some different substrate for this, as well as deuterated HFIP.
Deuterated one to see if the proton comes from the solvent or from the acid donor.
Yeah, right. We suspected, because of the work from UB, that the hydrogen comes from the solvent, and it also makes a lot of sense, really. And we wanted to look if it's incorporating where we thought it would, and it does. So what we see is that the acid activates the alkyne, and then there's a nucleophilic reaction. So the amide oxygen atom is attacking at the alkyne, and therefore the deuterium or hydrogen is incorporated into the molecule at the site of the former alkyne bond.
And the activation of the triple bond happens through polarization, right? So the acid does a similar job to the gold. Usually the gold would also activate this triple bond and then make the nucleophilic attack more easily. And the acid does the same job, or is it different?
No, you're perfectly right. So the acid is activating there. You could argue it works like the gold as well. So with the gold as well, you don't see a cationic species, and you also don't see it for the hydrogen attack. It would result in a vinylidene cation, and this one would have been really unstable. Therefore, you only have the activation and an immediate concerted reaction with it, not a stepwise one. And this also is in agreement with literature.
What I asked myself also when I read about the mechanism is, when you use the HFIP, the reaction works, and when you don't use it but use another acid, you get the brown sludge you mentioned. What is the role of the HFIP in this mechanism specifically?
Please bear with me. It's really something we don't really know. We did not see anything like that or had a study for this where we really see that's the effect and you can pinpoint it. We think that it has a strong ability of doing hydrogen bonds. So there are some stabilizing effects on different groups. And for example, in obese studies, they found through job plots that it's really bridging to ketones via hydrogen bonding. And you could argue that here as well. So every site which has some kind of negative or partial negative charge. So yeah, you could argue that every site which is negatively charged also can be stabilized by this kind of hydrogen bonding. But yeah, we didn't do a lot of extensive studies on this. It was more for us, or for me personally, that we wanted to explore the reaction more. And the mechanism stopped where we thought it would be sufficient. Yeah, it's all about time, really.
Yeah, I think that could be the PhD thesis on its own, just to find out the precise reaction mechanism. But it still is a very interesting concept that this solvent makes a catalytic reaction possible, which is not possible when you just use the acid that is created in situ.
Yeah, just as a disclaimer, again, my work is not catalytic in its own. So it's really, it's promoted. We didn't achieve a catalytic reaction. It was quite, no, not failure, that's too strong. But we were a bit displeased maybe that we didn't get down to catalytic amounts. You have to use over stoichiometric amounts, but not the great excess which was before this. So there's that. But yeah, nevertheless, it's not really catalytic, unfortunately.
Yeah, okay. So that was the plan, but the reaction mechanism in theory could be catalytic. But maybe some future improvements will get to the point that it will be catalytic. What do you think is the future of this kind of reactions?
So you basically scratching on is this really a sustainable solution? And I, from my perspective now, I would argue it is really not. It was an interesting topic to do research on, but it's not really sustainable. So you use a fluorinated alcohol to use the reaction. Yeah, as everyone knows, I think the European Union is going down on all fluorinated substances right now. So I think this was a bit, it will be outdated, basically, this type of reaction as well. I would look into different kinds of possibilities to do this reaction. For example, if you could do it in water, it would be interesting as well. When I first tried it, it didn't work out. So you get other reaction products. So the cyclization doesn't happen, but hydratization. And,
so swap out the HFIP with water and do the reaction.
Yeah, something like this could be done. Or if you had some kind of other solvent type in there, maybe this is something worthwhile. Also, from a sustainable perspective, most of my amides are solids, so ball milling would be interesting to do. Something like that.
So a complete different kind of reaction setup.
Yeah, at least would be interesting, right? We know it works in organic solvents, so this one is always there as well. And you could go to different kind of catalysts, for example. You could do... you could swap out the solvent. Yeah, there are lots of possibilities to work on this. Yeah. But for me personally, I would say, unfortunately, my type of PhD work will not see the great future.
That is often the case with this very basic research, where you do the research more out of curiosity and try to find out why things are happening, and this might not have a direct application at some point, but I'm sure it will lead to other discoveries which use the same concept in another way, which is the whole point of this basic research, I think. It has its own importance, although it might not have direct application.
Yeah, if you look into the unknown, you cannot be certain what you find.
Yeah, exactly.
Right.
Okay, that's a great note to summarize this episode. And in the next episode, we will look into another topic of your PhD thesis and all the learnings you took away from this work.
Thank you very much. Yeah, that's really something important for me, that there are so many things you learn through this. And yeah, that's really, everyone can tell you stories about their PhD, what they learned about themselves. And yeah,
sometimes more important
to it
than the scientific discoveries.
I think so.
Another thing you can learn from is the past. And that is what your podcast is about, also related to chemistry.
Yeah, then some shameless self-plugging of me. I also have a podcast, unfortunately not for the English listeners. It's in German, so I hope you could understand my bad accent. But yeah, my podcast is in German. It's called Alles ist Chemie, so all is chemistry. And it explores about chemistry and its history. So starting in the early ages of mankind with fire, we explore to now. I'm currently at episode 8 and had a very long break in between now. I prioritize different topics in my life right now, so a new job and so on.
Yeah, maybe we can also incorporate that into the next episode about the learnings for life.
Yeah. Yeah, I'm glad. Yeah, we can do this, right? I can say that there's a new episode which is scripted. I will start it up again, so I'm really happy.
Yeah,
about
great
this.
to hear this. I will be looking forward to listen to your new episode as well, and then yeah, thank you all for listening.
Yeah.
And we will come back to this topic in the next episode.
Thank you. Bye.
If you have an interesting topic to discuss in the podcast or have an idea for a topic with a guest you would like to hear, then let me know. Send me an email to podcast@innovateandreact.com. If you like this episode, please consider following on wherever you're listening to this podcast. Until next time, stay curious.